Welcome back to section 5.1. We're almost in our last chapter. Amazing kind of stuff, right? By now, everybody's getting a little antsy on social distancing and probably needs a little bit more math in their life. And here I am to help you. We're going to jump back and forth on mosquito larvae testing and this particular thing. And don't think that mosquito larvae is something that we need to learn, but we have to have some data to look at. And the question is, how do malaria parasites impact mosquito behavior? All right, well, we have to study things in order to understand how viruses move and things change. But let's start here with a little bit of a review, right? So the question is, for an normally distributed set of data on a normal distribution of 80, remember, that means 80 is my center value, and I'm standard deviating by 10. And the question asks me, what percent of this data is distributed for greater than 95? So it's telling me at 95, what's the p-value? All right, well, in your calculator, you should know that on a question that asks for p-value, we're going to do a normal CDF. And on that normal CDF, we're going to enter our lower boundary. We're going to enter our upper boundary, cut points, if you will. We are distributed on an 80 and a 10, so we have to enter that 80 and 10. We can't guarantee a 0 and 1 on this. This is not standard normal. And you hit the buttons on your calculator, and you're going to, and remember, the question here says what percent. So that's important, because when your calculator spits out an answer, it's 0.0668. Well, 2 spots over means approximately 6.7%. Okay? You don't round until after you turn it into a percentage. Bottom one, what's the p-value for a left tail test with a statistic of 9.0 on a center of 10? So I'm centered at 10. I'm counting by 0.8s. That's fun. 9.2. I don't need to go any further for an analysis because I'm looking for 9 and below left tail test. So again, now I just have to change my low point. So my normal CDF function again, -1 E99 is my low cut point. 9 is my high. My mu is 10. And I'm distributing on a standard deviation of 0.08 and 0.10, I think 6 when rounded. 1.06 unrounded. This one didn't ask me for a percentage. It asked me for a p-value. Okay. So the p-value is the decimal. The percentage is the percentage. So you get all this up here now. So we have these mosquitoes that were randomized to either eat from a malaria-infected mouse, exposed group, or a healthy mouse, control group. After infection, the parasites go through 2 stages. One stage is they're not yet infectious, days 1 to 8, and then in the second stage, they are infectious, days 9 through 18. The response variable, whether the mosquito approached a human in a cage with them. So our initial, our exploratory value or exploratory variable that we gave them was we either gave them the infected mouse or the non-infected mouse in the control group, and now we're measuring the response from that explanatory. And will it make them go to humans differently? So the mosquito approaches the human less often. That's big time, less often. So we're looking for things that are left tail. After being exposed, but before becoming infectious because humans are risky. Okay. So we have an HOO and an H sub A here. So first of all, our PC is our proportion of control who approach a human. Our P of E is the proportion of exposed who approach a human. So we're going to measure a difference in proportions. You should see that coming in those 2 groups. Our H of O is that if nothing's going on here, then the exposed group and the control group will be exactly the same. There's no different in human interaction. However, though, if there's something is going on, then if we take the exposed and the exposed will be less than the controls. And we're measuring, again, because it asks for less often. Now, we did the math for you, and this is not about the math because we should know how to do the math already. So in the exposed group, 20 out of 113 were measured, or 0.177. In the control group, 36 out of 117 were measured, or 0.308. And these are approaching and non-approaching. Okay, approaching humans, not approaching humans. And we get a statistic value of, or a difference in those proportions of 0.131 negative. It's important to know, and some of us have struggled with this, this is our statistic. Our statistic are not the two individual stats of 0.177 and 0.308, but the difference in those two numbers is our statistic that we're measuring. Now, if we made a randomized dot plot of this data value, okay, so I used StatKey, and I put in my two values. So I put in my 0.177 or my 20 out of 113, and I put in my other, and I subtract, and I ran them 1,000 tests, and I look at that data, and it's important to know that the center is null. The null is 0. Remember, nothing going on. P of E equals P of C. That's how I know this is happening. However, my alternative I'm measuring is that I want to see what's happening on the left side tail. Okay, well, calculation for me with the statistic I had of, remember, 131 was that statistic we had just a second ago. So I entered that statistic into the left side tail. Remember, that's my stat that I just showed you 10 seconds ago. Go back and look at it if you need to. And that stat produced that p-value. So approximately 0.9% of the time, the interaction is less. Okay, very small p-value, 0.009. What we're interested in is StatKey produced that very same value for us, and we were able to look at that curve. So what happens when we start to bring all these things together? Me doing the calculations, just simply doing the stats, me putting it in StatKey, or me putting it in the calculator. Well, what we start to see is that the observed statistic starts to come out quite often. For instance, this is the randomized dot plot. Notice the values and the difference of proportions. If we look at a second distribution, if we look at T, immunity, if we go back to the mercury in the fish, if we go back to the sleep versus caffeine, when we look at all of these, what do we notice? Well, we should notice one common theme. And it's not the data of any one particular one, but it's the smooth, symmetrical curving of the data. No matter what the data we measured on, no matter whether it was the mosquitoes, no matter it was the fish, if it was the tea and the immunity, or if it was the sleep and the caffeine, we had a smooth centered curve. It was roughly symmetrical and bell-shaped. And that's what we keep talking about. We keep talking about data performs, or data historically always travels in a smooth and symmetric measurement. So that's what we notice, I hope. Yeah, like they drew them for me. The normal distribution. So we can imply from that the symmetrical bell-shaped curve that we have seen for almost all of our distributions is referred to as the normal distribution. This is what we talk about when we say a smooth curve, if you will. Ooh, backed it up a little bit. So we have a new thing for you here. It's called the central limit theorem. The central limit theorem says for a random sample with sufficiently large sample size, and we'll discuss sufficiently large here pretty soon, the distribution of many common samples statistics can be approximated with a normal distribution. So if we have a sample size which is large enough, and we make many copies of that data, we should have a smooth, normalized curve. It says the larger the sample size, the more normal the distribution of the statistic. Sufficiently large will be very specific in chapter 6. Okay, specifically large will it be in chapter 6. Now let's just talk about the distribution. And we did this in chapter 5 and P5 especially, where we took a normal distribution and we described it by its mean and its standard deviation. Remember, our mean value is our center, and our standard deviation is how far out we go. If you look at the left-hand side, they have absolutely the same distribution as far as standard deviation goes, but they have a different center. Their centers are changed, and all that we have here is a shift. However, the curve on the right has the same center, but what you can notice is different is now we have a different deviation. The deviation has been changed. Now we have to undergo what's referred to as compression or stretch. I would hope that every one of you watching this in recent times of COVID-19, when we talk about flattening the curve, well, this is the one. When we flatten a curve, we control the spike of that curve. We compress data down. When we compress data down, we also stretch it out. Nobody's saying that the cases will go away. What they're saying is that if we push them out and make them flatter, we can respond to them in a longer amount of time, but we can do it much better or more rapidly. We can't control the growth, and the growth is out of control. We can't respond to the growth. Important to know that the area underneath all of these is equal. The area under every one of these different curves, no matter which curve we're talking about here, is 100%. We don't change the amount of area underneath of the curve. We just simply redistribute the area under the curve. So when we talk about a normal distribution of data, like so, for instance, a null of 0 and a standard deviation of 0.56. It says that we can, I want to jump one further ahead here. And I guess I should point to you. Your data of your 0.56 will be here. So you'll see that. And then your mean value you will always find in your center right here, if you're looking at a chart or a graph or something like that. Something to know, we can compare the original statistic to the normal distribution to find the p-value. So we can take something which was not distributed on a 0, 1, that's the standard normal, and we can convert it into that. We did that in chapter P5 where we found a z value. And once we found a z calculation, then we were able to change and do. This one is not a z because you can see that it's being distributed on a 0.056. And that's what we're going to do right now. It says if a randomized distribution is normally distributed, we can write it as n statistic comma standard error. What does that mean for us? That means that the p-value calculation from n, the null, right here, the null, comma, the standard error. It's the exact same idea as randomization tests, just using a smooth curve. So when we were running the dot plots and we were running thousands of different things and we were counting by different values and we were moving things differently, we were actually distributing on a normal curve. And remember, in StatKey, you can use your edit parameters to change your mean and your standard deviation. Don't forget, if you want to go lesser, you have a left tail design. And remember, here's your p-value from your statistic. And that statistic came from P1 minus P2 in this particular case. Let's go back to that z-score calculation and let's beef it up a little bit. So in chapter P5, we took a value of x, some statistic. We subtracted the mean, mu, and we divided it by the standard deviation. Well, we're going to replace that in a more generic format. Because the mean that we're talking about on a standard normal, all standard normal curves are centered at 0 and count by 1 on each side. all standard normals. So we're going to replace the mean value here with a null value. Well, remember that null value is always going to be 0, so that's going to make things nice. The statistic will still be the statistic, but the standard deviation will actually be the standard error, because remember, from here to here is referred to as a standard error. And from here to here is a standard error. So standard deviation and standard error are the same thing, but for us, they're always going to be a 1 in that standard error value. When we're calculating the z, we'll use the standard error of the given problem. Okay, so we'll use the statistic, the null, and the standard error. We'll put this to practice. It says often we standardize the statistic to have a mean of 0 and a standard deviation of 1. Again, we did that in chapter P5. How the z-score? So in the standardized value, so if we take the stat, we subtract the null, and we do the standard error. I want to point you for 1 second and make sure that all of you know where your stat formulas are. And again, I'm going to come out of here for 1 second, and I'll come back to it. So if I go into your home page, and if I scroll down through, and I go to student handouts formula sheet, if I open up that formula sheet, it's in a Word file. So when we refer to the generalized formula, of this, and I'll put this in a better read view so we can see it a little bit better. And let's blow it up just a little bit to make it a little bit nicer. Right here, general formula. See this general formula? And look across over here, sample statistic. We're now talking about a testing statistic. We're going to take the sample statistic minus the null and divide by the standard error to calculate z. So you have availability of this, or you have a reference, I should say, to this when you're working. Okay, so make sure this thing is handy. Also notice up here, we've already done this right here, right? We found the area by taking the normal CDF, lower, comma, upper, comma, mu, comma, standard deviation. We haven't done this yet. We've done endpoints, inverse norm, area to the left, comma, the mu, comma, the standard deviation. This is really nice. So we've checked off this, we check off this, we check off this. We're taking different things quite quickly. We also did this one here, confidence interval, sample statistic plus or minus the z-score times a standard error. And we'll do some more of that too. We've worked on this without the z value. Okay. All right. So let's go back to where we were. So we're going to go back to this data, and we're just referring to this data for a second. Okay. So just give me a moment and watch it happen. So we take the malaria and the mosquitoes from the original data set, and we had a negative 0.131. That's what we had. Okay. And when we did that data value, that was us just calculating, doing math. I took the first proportion minus the second proportion, and I got the negative 131. Look back at the video if you need to. The null hypothesis value is definitely a 0, because remember, nothing going on. From a randomized distribution, the standard error of the data, so when I did the data in StatKey and I ran it, I had a standard error of 0.056. This is not something you're calculating. This is something you're given. Okay, these are all given data values. So therefore, in order to calculate a z value, so I want to convert this thing to a standard normal. I don't want to know about negative 131. I want to know about standard deviations from the middle. I take the original data statistic. This is the one that we calculated by subtracting P1 minus P2. This is the null, or the center, because remember, that's the mean, because the middle is a 0. And I divide it by the standard error of the problem. Statistic minus the null divided by the standard error to get my standardized test statistic. And I get a z-score of negative 2.34. We'll start to know more about what that negative 2.34 shows me. It says compared to an n normal distribution 0, 1 to find the p-value. Okay, well, whether I use a calculator or whether I do this by hand, I can make this calculation happen. And I'll show you the picture here in 1 second. It says, and I just want to add to, if a statistic is normally distributed under H of O, remember H of O is your null, then the p-value can be calculated as the proportion of n 0, 1. So we're going to distribute it on a 0 center with a 1 standard deviation and beyond. Okay, the tails is what we're looking for. And again, this is in your formula sheet, so you have this. So here's this calculation of the randomized test. Remember, we ran this one, and I showed this to you. So I replace this with a smooth curve. I find the z number. So I do some calculations, and I smooth out, first of all, the data statistics and pull it into a smooth curve. Then I standardize it. Standardizing means taking it to the standard normal. So I use that calculation that we just did a second ago to find the z-score. And when I find that z-score, I get that standardized smooth curve. Notice that the middle of my curve is always at 0, and it counts by these really nice ones. That's what we want. Well, our z statistic was negative 2.34. Now remember, when we measure this, it's the area at the statistic and beyond. We used the words previously as extreme or more extreme. So the area is an incredibly low number, or the p-value is an incredibly small number of data which is actually as extreme as the observed statistic, 0.0096. It says the p-value is always the proportion in the tail or tails beyond the relevant statistic. This red data is the p-value. Notice that all of the tails in all three contain exactly the same amount of area, just they're reported in a completely different value. But 0.009, 0.0097, 0.0096, they're all identical. That 0.001 value difference change isn't going to mean anything for us. So for the data after the mosquito becomes infected, what's the relevant hypothesis? Well, if we talk about it, the proportion control, the P of C is the proportion of controls to approach a human. P of E is the exposed to approach a human. Mosquitoes approach humans more often after becoming infectious to pass the infection. So the question is, if nothing is happening, P of E equals P of C. If something is happening, now this is a different test than before, then P of E is greater than P of C. What we're trying to figure out is, for these mosquitoes, before they were infected, before they were aware they were sick, did they approach people? And then we take a measurement. And we want that to be less. But now that we know they're infected, so they're in this incubated phase of second control, do they approach humans more often knowing that they are carriers and they want to pass on the disease? That's really the question. So first of all, notice it's more. And we want to know in the question, is it more relevant? So I do the same calculations, right? This was the before, negative 131, and we already did that stat, and we did that control. Now we're doing the opposite of we're taking P of E and P of C. This is after the infection. Notice after. And we get a positive 151. So we're going to look at that data statistic on the same kind of thinking right now. This is just a different question, if you will. So this malaria now is being pushed out. And I know it's a right tail test. How do I know it's a right tail test? Look at H of A. H of A says greater, okay? It says the difference in proportions is 0.15. So when this calculations were made, it was and I think it was actually 0.151. I might have missed a 1 when I calculated. And the standard error is 0.05. The question is this significant? Okay, well, our first job, folks, is to first of all find the z-score. We need to standardize the data, okay? So first of all, remember, it's the stat minus the null divided by the standard error. This is our generic formula for calculating a test statistic, okay? So we take our stat, 151, or 0.151. We subtract 0. We divide by a standard deviation of 0.05. We get a z-score of 3. We go to our 3. We put date on and we color into here. A 3 is an incredibly high standard deviation. Remember, most data will fall, I'm going to change my color. Most data will fall between 2 standard deviations. This is where the normalcy is going on. This is extreme. This is wow. You get 3 standard deviations out on a piece of measurement or a test statistic, and you have found something happening. Now, if we wanted to calculate the p-value of that, we can go into either StatKey or we can go into our calculator. And remember, we now know the z-score is 3. So we could calculate the area to one side. So we could do an inverse norm. We could do, or no, sorry, not an inverse norm. We could do a normal CDF. And on a normal CDF, I almost tried to find area for you, and I wanted to really find that piece. We could find what that number was going to be based on the 3. Because remember, the 3 is the low. The 1E99 is the upper. And we're centering on a 0 and a 1. I'm going to do that with my calculator real quick off to the side. And you can do the same. So again, I'm going to second. I'm going to vars. I'm calculating area. So I'm using number 2, normal CDF. My lower is 3. My upper is 1E99. I'll leave a 0, leave a 1, hit paste, and here comes your p-value. I got a p-value of 0.001. Remember alpha from back in chapter 4? We now have a number which is lower than even a 1% alpha. We have found some statistical significance, just to let you know. So let's keep going here. So p-value, distribution. If distribution of statistic is normal, then the z, the sample statistic minus the null value divided by the standard error. We compare it to z, so we standardize it. We take this, the sample statistic, from the original data. We take the null from the H of O, and remember, the null is always nothing going on. And we take the standard error from the distribution. We have to have that standard error given to us right now. If the distribution of the statistic is normal, and remember, we're addressing this on what we want to refer to as a common scale, okay? A common scale kind of thing. Then by finding this, we should be able to compare this onto what we call a standard normal curve. A standard normal. We're trying to put it into p-values so that we understand +1 - 1, +2 - 2. We don't want to talk about other values, if you will. So let's do some questions. Let's actually get into the Wiley and see what we can do here. It says the following is a set of hypotheses, some information from one or more samples, a standard error randomized. So we have an H of O, P 0.29. So that's our H sub O, okay? Versus H sub A at 0.29. So we actually have a middle on this hypothesis of 0.29. We have an N of 800, and we have a p-hat measurement, or a statistic, of 240 with a standard error of 0.02. Find the value of the standardized z-score. All right, well, remember what we're going to do. In order to calculate z, we're going to take the statistic, 0.24. We're going to take away the H of O. Well, in this case, H of O is not 0. In this case, H of O is 0.29. That was our H of O. Remember, this hasn't been normalized. It's not sitting in the 0 category. And we're going to divide it by the standard error, which was 0.02. It matters if this number comes out to be positive or negative, okay? It's going to be a negative 2.5 is my z-score. Start visualizing that. Start visualizing that of where you think that is, and that's on the left-hand side of the curve, right? And remember, it's the left tail, if we need to know that. I see it, left tail. Round your answer. Okay, we did that. It might have been more, but I think I got 2.5. And that was it for that one. I got a z-score, and I'm good to go. Let's do it again. Question 14. It says, using this data for the proportion for fruit flies surviving after 13 days, and those eating potatoes and those eating conventional non-organic potatoes. So if nothing's going on, then the organic is the same as the conventionals. If something's going on, then the organic, we're looking to see if organic is more than conventional. I know it's a right tail test, and I read that from the center, right tail, and I'm testing to see if organic is greater than conventional. It goes on to tell you, kind of like what I'm saying, where P of O and PC represent the fruit flies, and we are at a 5% significance level, so our alpha level, remember that? Alpha level is measured right there. So if we can break that 5%, then we have something happening. So our first statistic. So let's get some statistics here. After 25 days, still alive. So here we go, 0.45. These are the organics. So I'm going to write down P of 1, P hat 1 equals 0.45. And my other one, my right over here, is 0.42. So my P hat of 2 is 0.42. Okay, so we have our two statistics. We have a standard error, and that standard error is given to be 0.032. Yep, 0.032. All right. So where's my sample statistic at? I'm going to change color here. So I can, that's my original stuff that I have. My sample statistic is going to be P hat 1 minus P hat 2. Doing that crazy line stuff. If I subtract those two values, I get 0.03. Now what do I got to do? Now I got to calculate a standardized score, my z-score. My z-score calculation is going to be the statistic, the subtraction, minus the null. Okay, well, what's the null? The null comes up from here. P0 minus PC equals 0 because nothing going on, divided by the standard error, 0.032. And when I do that math, and I do that calculation, I get z of 0.94. Z of 0.94. So let's go to where we can actually enter some questions. We're not quite done yet, but we do have a 0.94. So round your answer to 2 decimals, 0.94 for our z-score, right? Okay, good so far. Secondly, what is the p-value? Okay, well, the p-value, I'm going to have to actually use my calculator to get this. So I'm going to calculate my normal CDF value. And remember, I'm looking for the tail, which is greater. I got that from the original value, okay? So I need to calculate my 0.94 statistic and beyond. So use your normal CDF function. And I'm going to stall my computer for just 1 second because I have to reboot my calculator. Give me 1 second. All right, I was able to fix that for you. And here we go. I rebooted the thing. So again, I want to calculate that that normal CDF. So I want to go a second. I want to go vars. I want to go number 2 for normal CDF. Remember that my cutoff was a 0.94. So I'm going to use a 0.94. Remember my value going to the right is my very large 1E99. That puts me way to the right. I know that I'm on a 0. I know I'm on a 1. I'm going to paste that thing in, and I'm going to get approximately a p-value of 174.174. So I'm going to go back here, and I'm going to start from the current slide, and I'm going to add in my numbers. So far we have a 0.94 for my z-score. I converted that into a p-value, which was 0.174. And now it asks me, what's my conclusion? Okay, well, here's my conclusion. Here's my p-value, 0.174. And remember, when I am looking at that, I'm comparing that to the alpha level that we talked about earlier, 5% alpha level. The p-value is greater. Remember, the p-value always has to be smaller if you're going to reject. So you do not reject. Your p-value must be smaller in order for you to reject. So your answer is, do you have evidence? No, you do not have evidence. Okay, p-values have to be smaller in order for you to reject a data value. I'm going to, I think, skip this one. I'm going to skip this value here. I'm going to skip that one. On these, and I went just a little too far. When you go into Wiley questions that have these different symbols that you have to pick from up here. Oops, sorry. When you have to pick from these different symbols that are up top, it keeps moving on me. It won't let me write or anything like that. Right here. Then make sure you use this edit button right here. And that edit button will give you a drop down and let you roll down through the different values that you want to pick and what you want to put into your expression. Okay, so maybe you want to pick h of o is equal, maybe you want to pick h of a is greater or less than, and the top one is just the expressions that you can use. Okay, you can't type them in, you actually have to use the edit button. All right, we, I believe, have wrapped up what we need to for this section. We'll move on to the next one, and I'll make that for you. If you have any questions, let me know.